parts. One is after the Shilpa Sutra talk. Now it is going to be about contributions of the Jaina from the Jaina tradition. So again, the Jaina tradition also flourished around the same time, the first millennium, a little later than the Vedic period, of course. Uh, Mahavira, who sort of rejuvenated in some way the modern Jainism, is from the 6th century BCE. And the some of the early Jaina mathematics seems to have flourished soon after him, actually. And Mahavira himself, according to legend, was a mathematician of some sort. Of course, though I must say there's no concrete evidence of his particular contributions or even his teachings as far as mathematics is concerned. But nevertheless, the subsequent acharyas and so the Jain priests, they attribute a lot of things to him. Apart from philosophy, they attribute also the attitude to mathematics and some of the mathematics itself to Mahavira. So now let me begin by opening my presentation. Yeah, so as we all know in India, of course, that Jainism did not engage in any rituals. In fact, it was meant as a kind of antithesis to the Vedic ritualist tradition. And so one might wonder what their motivation was for geometry. So and it turns out again that it is, though it's not about rituals, about the spiritual aspect of Jainism did contribute to the rise of mathematics. So the Jaina scriptures are estimated to be from somewhere between 5th to 3rd century BCE. Again, just as in the case of Shiva Sutras, I should say these dates are on not very sound basis. This one European German researcher, Hermann Jacobi, is attributed these estimates based on linguistic considerations, etc. But on the other hand, I must say Jacobi's estimates for other things have been way off the mark, so one cannot really depend on that. But nevertheless, from from a historical perspective, it sort of seems reasonable that this would have been the period when they engaged in mathematics, the kind that we are going to talking about. Now, another thing, of course, you know that the Vedic tradition was quite completely oral for a long, long time, until very recent times. On the other hand, the Jaina tradition was also oral until some point, but they used to have these periodic conferences, and at one such conference in 454 CE, that is not BCE, 454 CE, there was one major conference during which they decided that this oral tradition is somehow inadequate, and then they decided to write down many of the things. So in some way we have some, well, not in any strict continuous pattern, but in a certain sense we have a tradition of written material coming from about the 5th century in BC. Not that the original 5th century documents survive, but one would assume that they were the ones who subsequent precursors of the later versions, etc. So anyway, we'll not go into these fine historical details, but this is just the overall perspective which you can keep in mind. Now, the way that they got interested in mathematics is the following. The terrestrial world, the world as we see it, was conceived to consist of, you must have come across this term, of course, in India, everybody knows it, Jambudvipa. Jambudvipa is sometimes people think that Jambudvipa is India, but it's not. Jambudvipa is the earth. And Bharatavarsha was in fact the name for our subcontinent. Of course, there's no well-defined geographical contours, but the region was known as Bharatavarsha. Jambudvipa, the earth, was in the shape of a flat disk. I mean, in the Puranic tradition, you would know that with the earth was somewhere is flat and is supported by Shesha. So this is something similar. It's a flat disk. The legends about how it is held, etc. But apart from that, this Jambudvipa, it's first of all, it's a flat disk with a huge size of 100,000 yojana and in diameter. And this it is according to their conception, this is surrounded by a ring of water, which is twice the size of that. And then again, there's a ring of land which is twice the size, etc. And this is supposed to extend ad infinitum, I mean, indefinitely, so to speak. So, if you sort of, if you are mathematically inclined, you would see, from viewing somebody from that period, you would see that there would be two things in this model which are kind of significant. One is the circle, and the from a geometric point of view, and then another thing is the stretch of rings going to infinity. So on both these themes, they seem to have made some progress in mathematical terms. And here, of course, I'm not going to talk about infinity. Infinity is a totally different ballgame, but we'll talk about what they thought about the circle, about the circle, geometry of the circle. So apart from the Jambudvipa, the Earth itself being a flat disk, there is also thing about say the kind of conceptualized geographical details, I would say. I mean, it's not the real geography, but the Earth was sort of divided by 7 mountains which ran parallel to the equator. So, and then that made that provided to the fodder for thinking about chords in a circle and distances and so on, various things. So that's in a nutshell. This is the motivation for geometry in the context of the Jainas. So I mentioned the 7 mountain ranges running parallel to each other. So okay, so coming to the sources, there are various works. It's called very ancient ones. Again, as I said, the periods are roughly estimates based on secondary considerations, etc. The works are this Chandra Prajnapti, Surya Prajnapti, Jambudvipa Prajnapti. These are some of these works are actually primarily philosophical in some sense about the world as a whole, and as a part of that, you will it is one comes across some amount of mathematics in that, and it's not like any mathematics chapters, but things sort of strewn in between, where you see that the philosopher author has views some of these mathematics in a sort of is a respectable subject which needs to be transmitted and so on. So so therefore we do not have any kind of textbook literature that one would find in the Jaina tradition. I'll comment a little more on this as I move on. Then I mentioned the earliest ones, the Chandra Prajnapti, etc. Then there is a Sthananga Sutra, which is another important reference. Bhagavati Sutra from Sudharma Swami. These are again both from around 300 BCE. And Shatkanda Agama, and this was by someone called Pushpadanta and Bhutabali. I mean, some of these have dual authorship because not that they collaborated in the way we do, I think, but some original part of that would have been expanded by later authors. So sometimes there are multiple authors, meaning one elaborating on one, not elaborating, expanding and completing the version in some way. Then there is Tattvardhadigama Sutra Bhashya of Umaswati. Umaswati is one of the most important figures that pops up in the Jaina literature. Again, Umaswati himself was not a mathematician; he was a philosopher, but he does pay rich tributes to, in some way, to mathematics. Now, this is from the early period. So you see the time frame going up to about the second century CE of our era, and after that there seems to there's been a lull for several centuries. There are some names. I mean, if you go through the actual, I mean, the Jaina details and so on, they list various other names also, but they do not have not featured in, say, major historical accounts from outside the Jaina tradition itself. But until about the 8th century, where we come to here some of these later names, and here some of the important names are Sridhara. Uh, okay, yeah. I might mention at this right here that there's for quite a while there is some ambiguity about whether Sridhara is from the Jaina tradition or not. Uh, and in fact, yeah, about his period also there is some confusion. But now this seems to be granted. I'll not go into the more details about the controversy, etc. And it's is supposed to be from about around 750. There's also some argument about it could be a little later, but essentially they're definitely in the 8th century. And then the Mahavira, of course, is I think better known because of the Ganita Sara Sangraha, which I think part of the reason was that it was edited with some I mean, there's reach support for that, and then it has been better known in some way. And then Mahavira is also, even in terms of the Jaina tradition, I think maybe he is better known. Anyway, so aside from such minor details, so then there are also other Jaina scholars who contributed. The Veerasena with the 816 is the name of the work. Dhavala is a commentary on the Shatkandagama that I mentioned. So, and Nemi Chandra, this is the his work is Trilokasara. And again, now as I have left here, there is a sort of gap, and then another important name that is known is Thakkura Feru. So Thakkura Feru comes from this is after the Islamic rule had settled in India. So this is, and in fact, Thakkura Feru served as as a treasurer in the Sultanate at Delhi. But he was his Jaina training and as well as work and so on. So and so while there is some influence seen in the effect of the change into Islamic ethos, so in some ways, the much of the mathematics that he exposes is from the Jaina tradition. So the okay. The original results in many cases are from the early works, and here these scholars have had a great pedagogical impact. So, for instance, I mean, though I'll not dwell on this later, but so a lot of learning of mathematics, I think, was sustained by these works. And for instance, you see that Mahavira is from the 9th century, and until Bhaskaracharya came into the picture in the 12th century, this was one of the major works, where mathematical works which people depended upon. So. And similarly, Sridhara is known not exactly at the textbook level like Mahavira or Bhaskaracharya in the Siddhanta tradition, but he's very much referred to in scholarly circles in terms of the reference in the later contributions. For instance, even Bhaskaracharya, for instance, refers to Mahavira has in fact many things common in his works and so on. So Sridhara, Mahavira, they had a big impact in terms of rise of learning and dissemination of mathematics into the general practical world. I mean, much of the mathematics in the earlier, so as you would see, the Shubha Sutras or the early Jaina tradition, they had to do it basically with some limited objective, namely the spiritual aspects and then things related to timekeeping in the Panchangas and so on. Whereas in the later centuries, as trade flourished, arithmetic became very important. They had to do calculations, they had to understand geometry for various reasons. Then many problems of algebraic type came into acquired importance. So it became the mathematics became important not only for the limited circle but a much wider circle, and in sustaining that, the Jaina scholars played a very important role. Okay, so now let's come to the subject matter. So, firstly, let me. Maybe I already mentioned this in another context, but here is something. In all the ancient civilizations, it was common to take the ratio of the circumference to the diameter to be 3. This is seen in Chinese and the Hebrew tradition, biblical tradition, and all, also in the in early Indian tradition. The Shulva Sutras in the Bodhayana Shulva Sutra, for instance, there is a verse which indicates that it's a passing reference, but it indicates that the circumference to diameter ratio was taken to be 3. Now, the Jaina tradition quite early moved to a closer to another value, closer value, so to speak, so to pi, and they adopted the value square root of 10 for pi. For the ratio of circumference to the diameter, they adopted the value square root of 10. Now, this value square root of 10, which is about 3.16, etc., you can work out the decimals. This involves an error of about 2 by 3% in excess. It's in place of 3.1415, etc. It is that. So, from the correct value, okay, so I mentioned. Thus, and it's interesting to see how, in what ways it featured in their practice. So, the circumference of Jambudvipa, as I already mentioned, that the Jambudvipa was supposed to be of diameter 100,000 yojana. Many of these things kind of came as metaphysical thought rather than measurements, of course. But given that the diameter was meant to be 100,000, they calculated the circumference as by taking, you multiply. So it's not that you take square root of 10 up to some decimals and you multiply the decimal fractions were not there in India until very recently, until the recent centuries. So the what they would do is multiply. So this is the diameter. You square it. You multiply by 10, which is now, as we would write it, it is 10 raised to 11. That's a certain 1 with 11 zeros. Of course, writing 1 with 11 zeros was present. I mean, decimal system has been there in India from since the very early times, and probably the Jainas were the ones to make use of it extensively. I think there are many such calculations seen in the Jaina works, Jaina canonical works. So anyway, that's a separate topic. We'll not go into that. So and then let me just mention that it is given to be. So let's look at how to what accuracy to degree it is calculated. So it's first of all three. Uh, the 3,16,227 yojanas. So of course, the factor of 3. Then the remaining part is computed in smaller units, this Gavyuti, and then still smaller unit Dhanu, and still smaller unit Angula. So here one yojana is 4 Gavyuti, it is 8,000 8,000 Dhanus. So each Gavyuti is 2,000 Dhanus. And one yojana in effect is 768,000 angulas, so 768,000 angulas. So it's calculated to a very fine value, and at the end of it again, it is also mentioned that as a and a little over. So I mean, it's because the tradition of finding square roots to accurate degrees is something that goes back to very ancient times in India. So in the Jaina tradition. Okay, so the value square root of 10 had great longevity and was in use in India for 2000 years. I mean, if one of course assumes that it started somewhere around 500 CE, then it did go on until 1500 or even 1700. I'm coming here. So now in in the meantime, of course, the better values did come to be known. So Aryabhatiya, as we will see, or maybe you would already know, introduced the value 3.1416. It is not in decimals, but as the diameter of given by giving the diameter of a circle of 20,000 units. Which is exactly which exactly corresponds to taking the ratio to be this, not by approximation. It's given to be this, which is an approximation, mentioned to be approximation. In the Jaina tradition itself, in Veerasena, who wrote in 816, introduced another value 355 by 113, 113. And this turns out to be even more accurate. And where is it? One doesn't exactly know. I mean, this is the value was also known to the Chinese before that period, and it seems likely that the Jainas somehow it got it from the Chinese. It's probably of Chinese origin. Now, it was used not only in the Jaina tradition, but it also in the Siddhanta tradition, including by Brahmagupta. So, Brahmagupta takes the value to be square root of 10, and it's even found in some important works quite late in the until much later in the Siddhanta tradition. There's a work of Kamalakara, the Siddhanta Tattva Viveka, and this is from the 17th century. And there also, the square root of 10 is taken to be the value of pi, and there's been some criticism that it is this kind of orthodoxy stretched too far some way. Until okay, so along with the Indian arithmetic, as which we have transmitted to the Arab world, this value reached the Arabs and is found in Al-Khwarizmi's book on algebra. And from there, it also entered European mathematics, and where it's supposed to have been used until quite long. Now, somewhere I remember reading that in Europe also it was used until the 15th century, but I have not been able to confirm this. But it did get into the European mathematics, but I don't know to what extent it was prevalent and how far it lasted. But certainly, it was something taken as routine to use square root of 10 as the value for pi, as we now, for instance, do. For instance, to take 22 by 7 as the value. Okay, now. We are going to talk about the geometry of the circle. Here, so consider a circle with diameter d, the chord of the circle. So we see my diameter, and this is the chord, And now if you think of this chord and the arc, you'll think of the bow. So this is called this combination is called the bow figure. And yeah, again, extending the imagery, this segment from the midpoint of the chord to the midpoint of uh, the arc is called the arrow. So this is the chord, this is the arrow, and this is the arc. So and this of course the diameter. Now, one of the first things that one finds in the statements is that this chord C is equal to square root of 4 times the uh, arrow times d minus h. So the c square, the chord square, in other words, is equal to 4 times the 4 times the arrow and d minus arrow and d minus arrow. So this is elementary. One would know this from you'd all know this from elementary geometry, and one way that one would I mean, from in the background for our own training, it should sort of seem natural to deduce it from by properties of similar triangles, etc. That you can when you see that this is a right angle, and these are these are similar triangles. And triangle, this triangle, and this triangle are similar, and then if you from that you can see the ratios, you readily get this thing. However, another way of doing this is by using the Pythagoras theorem. If you so I mean, there's a this is a right angle triangle, and using the I'll not go into the computations. It can also be seen from it's a simple exercise to do it using the Pythagoras theorem. So said here, and it's I think generally. Uh, I believe, and so also is the standard narrative. I think that the formula is likely to have been deduced from the Pythagoras theorem, and for sure they would have they knew the Pythagoras theorem. First of all, I mean, we know that the Shulva Sutras, which preceded some of this activity, already mentioned the Pythagoras theorem. And though, I mean, these traditions with the Shulva Sutra tradition and the Jaina tradition may not have any deep and rigorous interaction, nevertheless, some of this information of this kind did get transmitted, diffused into each other's knowledge systems. So therefore, and another thing I'm going to say is that the later formula for the arc that I'm going to talk about also readily shows that they would have been inspired by the Pythagoras theorem. So surely they would have known, they knew the Pythagoras theorem. So from that they could deduce that this relation holds. Now, and going back to one of my earlier comments, we don't have the textbook kind of data or information about their findings. So, for instance, nowhere do we find any statement of Pythagoras theorem or how some of this was deduced. So, these interrelations, they occur simply because there is a certain. So here there is a chord involved, which is this refers to the mountain range, and this is the arrow is where it is kind of located vis-a-vis its the position, and so there is the calculations about something that the interrelation between the things that they were talking about. So for the Jambu Dvipa, the diameter is known. So and each mountain range has its chord, and the arrow. So in terms, these are the interrelations about what they were actually. The was a topic at hand in some way. I mean, they're talking about the word and giving the interrelation between some of these things, and what what went into these calculations, we would not know. We do not know. not enough details available on that. Okay, so roughly the Pythagoras theorem and its applications in some way was of various kinds of, especially these formula are in fact mentioned in several of the Jaina works. Many of those which I listed, each of them would have statement of well, maybe not each maybe a strong statement, but many of them have this thing. So it's a multiply exposition topic. So something that they considered sort of important to pass on to generation after generation. Okay, now yeah, going from these straight segments, the chord, the arrow. One would also there's also the formula for this arc, and this is something that I especially like to talk about uh, for reasons that will soon become clear. So yeah, it's going to be a more intriguingly, they had a formula for the arc A. Arc is A in terms of the chord and the arrow, and I like to bring it to you in the original. Usuvagam Chaguniyam Jivavagammi Pakhivitanam Jam Tasya Vagamulam Tam Dhanupattam Vyanahi. Now, surely you recognize that this is not Sanskrit. The early literature is in Prakrit, which was one of the important languages of ancient India. So, okay, so the Usu Vaggam, Usu corresponds to issue in Sanskrit. Vaggam is Vargam, and so the square of the arrow and Chaguniam, you can recognize Cha is 6, Guniam is multiplied by 6, etc. And so maybe ultimately maybe I'm not going to spend time on interpreting each word. Uh, so the formula tells you that the arc length of this arc equals square root of 6 times the arrow squared plus chord squared. Jiva is the chord. Jiva Vagam is the chord squared. And yeah, so Dhanu Patta, Dhanu, again you recognize is Dhanu, and Patta is the extent. Vyana is it's known, it's kind of Viduhu appears in many Sanskrit verses. It's Vyana corresponds in Prakrit to that. So here is the formula which gives you the length of the arc in terms of the length of the chord and the length of the arrow. Okay, so now I say that this is inspired by knowledge of Pythagoras theorem in the following sense. If you look at, so here we are thinking of the length of this arc. Now, if you think of the length of this path, which going from A to C and then C to B, okay. Now that you can calculate using the Pythagoras theorem. So the square of you know that the square of this equals the square of this plus square of this, and you have to you get the account for this. You have to double that. So in all, you will get with this as C and this as H. You will get it is 6H square plus 4H square plus C square. So half of this squared plus half of this squared and multiplied by 4. So you will get 4, the length of this path you can calculate to be 4h squared plus c squared. And one would recognize that, of course, it should one would expect that this thing is something similar to the rectangle triangle, but it has to be something more. Now, let's make a guess. Is what one would say. So something more has to be added. Now, why 6? You might wonder why 6, but then it's once you know that once you are looking for some constant here, some number here, then you look at what should happen for the diameter, and to match, if you try to match it what it should be for the diameter, it turns out that it has to be exactly 6, because notice that that's when you would get there. So the circumference is square root of 10. So the half of this will be the arc corresponding to the diameter. So you will have square root of 10 divided by 2, and that you will get for the diameter when c is the diameter and h will then be the radius. So the correct matching factor you get for that is 6. So combined with the fact that that we are looking for a formula which is similar to what is suggested for this by the Pythagoras theorem, and matching it with what is expected for the diagonal, they would have arrived at this formula. This is of course just speculation, but very plausible is what I think. So, okay, the some of this I already said. Yeah. Now, so for this is the length of that straight line path, and then the raised one is the path is given as the length of the arc. Now, interestingly, a similar issue was addressed in the Greek literature by Hieron of Alexandria. Hieron is a very famous engineer in the Greek tradition, substantially later than the famous names that we know, Euclid and so on, but from about the second century. And in some ways, Hieron was of a somewhat different tradition than the pure mathematics of the Pythagoras and Euclid's tradition. They were being an engineer in some way. I mean, having applications in mind, he had often to resort to approximations and so on, try and approximate things, etc. And among his work, Geometrica, addresses the similar issue. What is the arc of a circle given the chord and the arrow? And Hieron had proposed first approximate formula 4h square, square root of 4h square plus c square plus 1 by 4h. So he was simply making a linear an increment of 1/4 of h to what you need for the straight line path, which I showed. And then apparently he found that somehow this was not very accurate, not good enough. Then he proposed a more refined formula, square root of 4h square plus c square. First, you multiply this by a factor 1 plus h by c and subtract h. Now, I'm afraid I don't know whether even the motivation for this is known, but these formulae are known. This is from the book of Heath, for instance, which is a exposition of Greek mathematics. So now so given such a situation, of course, one would like to compare and how the formulae of the Jainas compared with the formula of Hieron. So here is a table which shows my computations for 15 degrees. So the actual arc length value is this. The Jaina value is given by this, and Hieron's first value, Hieron's second value. Now you see in most of this range, and in parentheses I have marked how much it differs from the actual value. This is Uh, this is an excess by 0.007, whereas this is an excess by 0.07, etc. And in most angles, you see that the Jaina value turns out to fare better than the Heron's work. On the other hand, somewhere near here, for instance, here the error in the Jaina value is substantially more, whereas the Heron seems to get it very close. So on the whole, they seem to fare quite well, except though not consistently good as one would might might expect. Okay, so yeah, I think with that, let me move on to the these are we now come to the second part of the Jaina contributions. I delineated the two parts, so and some gap. One doesn't know quite the historical reasons for this thing. So now now the period that we're talking about, you should remember that this is post Aryabhatta, Bhaskara the first, post Brahmagupta, and all that. So naturally these people not don't know whether I can say naturally, but the people did have the benefit of the developments that had occurred in terms of growth of knowledge. And though in the tradition there is not always the attributions given to etc., but I mean for simply maybe for it can be simply for the reason that the learning was by word of mouth, and you didn't there's no citation etc. that was consistently maintained. So and this is sort of a common feature in many ways in ancient mathematics. So we should not think of it as any plagiarism or anything. So okay, so uh, and the thing we're talking about is mainly about their exposition and some of the new contributions that they are like seem to have made to the overall stream of building the geometric theory. So the my what I'm going to state basically is only the highlights, which are and not going to the nitty gritties of how geometry was done. I mean, for want of time. So the in the context of in Indian mathematics, the credit for the first correct formula for volume of sphere is generally given to Bhaskaracharya. Bhaskaracharya's work, which we'll talk about later in the afternoon. The volume of the sphere is, is described and essentially in terms of what we now know as the formula, and this is in the 12th century. Aryabhatiya has gives a formula, but it's actually incorrect for in a very peculiar way. So we will not discuss that. It turns out, however, that the formula described by Sridhara in his work Trishatika, in this respect, is actually correct in spirit, let's say. And let me explain what I mean by that. The formula he gives is the following. He gives the formula for us, given the diameter of the sphere to be d, he gives the formula for volume as half of d cube times 1 plus 1 by 18. Now, I say that this formula is correct in spirit because 1 plus 1 by 18 actually corresponds in a very natural way in their context to 1 by 3 pi. Remember that this notation pi did not exist, or even thinking of a particular constant and saying that multiplied by this constant, this framework did not exist at that time. So people had to either write it say it in words that is circumference times that, or used to use approximations. So 1 by 3 pi is corresponds to 1 plus 1 by 18, and if you substitute this one, if you think of this 1 plus 1 by 18 as pi, this corresponds to 1 by 6 pi d cube, which is the correct formula for the for volume. And why does 1 plus 1 by 18 correspond to 1 by 3 pi? Notice that, so 1 by 3 pi is 1 by 3 times square root of 10. Pi for them was square root of 10. And so this is 10 by 9. And then so it's 1 plus square root of 1 plus 1 by 9. And this is the very classical formula that this approximately equals 1 plus 1 by 18. So since the Sridhara was writing for the potential users, is probably preferred to give a fraction rather than just the description in terms of geometric notions. Okay, so another thing I'll mention is Veerasena's formula for the conical frustum. So in his Dhavala Tika, Veerasena gives a formula for the volume of a conical frustum, and so with diameters A, should have a picture perhaps. Diameter A at the bottom, B at the base and the top, A at the base and B at the top, and then the height H. We have a conical frustum with cone chopped off at a certain height. So, and then the volume is given to be this. This you recognize is the correct formula for which we study in coordinate geometry, for instance. That is the correct formula for the volume of a frustum. So, one speciality is that, unlike in much of the extant ancient and medieval literature, we find here a description of the method for determining the volume. It is, it's again, it's as you would expect. It involves summation of an infinite, some kind of infinite series expressed in some way, and the idea of infinitesimals, which is sort of akin to calculus. Of course, similar ideas are found, they're reminiscent from in older works also in other cultures, and that's Archimedes, for instance, again has used method of exhaustion. That's what this corresponds to in some way. And in China, Liu Hui also used similar methods, etc. But in the Indian tradition, this is a very first clear manifest expression of the method of it. Sridhara, sorry, this is Veerasena from 816. And one may speculate that perhaps Bhaskaracharya may have been influenced by this kind of work. Let's move on to Mahavira. Mahavira's ellipse. So Mahavira is his book Ganita Sara Sangraha is well known, and this is an exposition of various things, including starting from arithmetic, geometry, and everything. Puttaka method that we talked about is also included, and so on. So it is more it's a comprehensive work for that period. And Mahavira also specializes in talking about figures which are not standard. Something like conchiform, shankha. So the shape of a shankha, or say the tortoise back, and so on. So unconventional or curved shape of a ring, and these are the formula are not exact. They're approximate, but nevertheless the idea of talking about these and saying something, to be able to say something meaningful. Reasonably good approximations or worthwhile approximations for practical purposes. So he gives formulae for, among other things, he refers to a figure called Ayata Vrutta. Ayata corresponds to actually rectangle. This is the word used for rectangle. And Vrutta, of course, is circle, rectangle, circle. So roughly the idea is to talk about oblong circle. That's what would be the appropriate interpretation, oblong circle. So the figure under consideration is a rectangle or oblong circle. The term is has often been translated as ellipse. I mean, many standard texts, which I don't think is correct at all. Uh, uh, okay. For one thing, it is there's no, unfortunately there is no description of how the figure was constructed, nor is there any geometric characteristic that is described that would pinpoint to the circle. It's only meant to be an oblong circle. And what do we learn about this oblong circle, whatever it is? Here are the formulae for its circumference and its area. Okay, now for the circumference, the he invokes two parameters, ayama and vyasa. So ayama is there's a certain axial symmetry is was implicitly understood. So ayama is the wider side, vyasa is the smaller side, and so the circumference of the figure is given to be 2a plus b. Ayama is taken to be a, vyasa to be b, and the circumference is the in approximate measure. Well, I should have mentioned to you one speciality of Ganita Sarasangra, that there's a separate section where first approximate values for various things are given, and then there are more accurate values described. So there's what is called sthula and sukshma values. So as a sthula value, rough value, it is given to be 2a plus b, and the more accurate measure is given to be square root of 4a square plus 6b square. Now it's interesting to note that okay, the two formulae are seen to correspond to viewing ayata vrutta as the shapes shown here. So this the shown here, the bottom figure is a join of. Okay, the first one here, this is here. I think I not said it in words here. This figure is you take two semicircles and then join them by this rectangle. Join them with this stretch of two lines. So this diameter of this semicircle B. So you have one full circle with B, and then the rectangle with A minus B. And if you add the rectangle with one side A minus B and the other side B, and if you add the length of these two and this circumference with B, you get precisely 2a plus b. It is the circumference of this figure that is given. So whatever the ayata vrutta had in mind, the approximate measure of that is calculated to be by this figure. The story about this is interesting because it goes back to the classical ancient Jaina period. Now the figure here is simply these are two bow figures joined to each other and just smudged out here. So they ignore the tip cusp that will be formed here. So there is the join of two bow figures. Now if you in this bow figure, this side is A, and this is B by 2. Now if you use the earlier formula for the arc, okay, then that will come out to be A square plus 3 by 2 B square. So that will be the formula for arc in the ancient Jaina formula, according to the ancient Jaina formula that we calculated. And double this, that is what is given as the fine measure. So it's the figure. Therefore, in general, I think the message actually was that if you had a figure which is not exactly circular but somewhat oblong, then definitely you can you can think of the axial measure, the longer side and smaller side. The approximate circumference of that will be like this figure, whereas the more accurate estimate will be given by this figure. I don't think there is anything to do with ellipse in in the strict sense that we learn in geometry, which goes back to the Greek tradition. Okay, now there's also a formula, as I mentioned, there's also a formula for area, but we'll not go into that. First of all, I think has been a subject of some interpretation. So it's if I begin to say something about that, say about various things, etc. So I'll skip that. There's a similar formula, similar in spirit. I mean, it's for area. Okay, so now, here are some concluding remarks. The extant early Jaina geometry is deeply embedded in religious and philosophical works, so much so that it's difficult to get a comprehensive understanding of the mathematical part beyond the isolated results that we know. So, while geometry seems to have been recognized as an important pursuit, what they did with it is not clear, not clear enough. Uh, and some of the later Jaina works, especially those of Sridhara and Mahavira, are, on the other hand, were evidently inspired by needs of practical life, and they're bolstered by the cumulative knowledge that had accrued by their time. Now, where seems to be little common ground in the pursuits between Shilpa Sutra and the early Jaina works. Of course, there is the Pythagoras theorem, which is common factor, but not much else actually. In terms of constructions, in terms of how they would go about doing things, etc. The later Jaina scholars seem to rely to a great extent on the theory developed by the Siddhanta tradition. For instance, I mean, not only in geometry, but for the Kuttaka and all that is explained. So, in a way, they were not just continuing the Jaina tradition, but being expositors in a global way. I mean, taking a global view of coming from a tradition, but taking a global view of mathematics as it stood at that time, and giving an exposition and making certain contributions along the way. And I'm not said anything about Ferru, Takura Ferru here, but he also improved various formulae, for instance, in terms of these coefficients, etc. I mean, we talked about volume formula for of Sridhara. There are similar formulae for area, this, that, etc. And Ferru made some improvements in those respects. So there are upgrading of knowledge was occurring with each of these authors, though one did not see any fundamental change in perspective. So they have contributed greatly and to what emerged as the mainstream Indian mathematics. So with that, I'm concluding the session for today with Jaina mathematics. Next time we'll be talking about the Siddhanta tradition. So thank you. Not next time is this afternoon.
Hello, thank you, sir. So, Khatri sir, any comments?
Yeah, only one thing that the formula for volume given by Aryabhatta was not correct. That has been mentioned, and Sridharacharya appears to be the first one who has given somewhat correct formula. But in between, there were some people like Bhaskara one and Brahmasputa Siddhanta, of course, was there. Brahmagupta. So did they give
those formulae are approximate? They're not correct.
They are not correct, but they at least gave some formula.
Yeah, but they're I mean, Aryabhatta's formula is off by a very large factor in some way, but whereas these are some reasonable from a practical point of view, they are reasonable approximations given in Bhaskara 1. Actually, Bhaskara 1 is also likely to have come from Jaina. Bhaskara 1 in various ways seems to draw upon Jaina scholarship. And possibly the Bhaskara first formula for volume also is possibly from the Jaina tradition.
I see. Thank you.
I didn't go into these various details.
Yeah, right.
हा येते हा येते कुठलं
Any other questions? Comments?
Hello.
Yeah.
Ram sir, are you here?
Are you there?
I think he is not here.
Yeah,
Any other questions from audience?
Visible. Hello?
Yes, any other question from audience? Sir, it seems there are no questions, so we will stop this lecture at this time, and there will be 15-minute break, and next lecture will start at 12:20. And the speaker is
Next lecture.
Dr. Venkateswara Pai from ISET Pune.
कोणाचं आहे पुढचं पुन्हा
Dani sir,
Yes?
so your lecture is at 2:30.
Yeah. Right.
So we can take 10 to 15-minute break now, and then we will start the second lecture
Right.
at 12:20. Okay.
लोक सोडायला लागले बरोबर बरोबर सोडायला लागले
हे किती होतं?
तुला मायक्रोवेव्ह मध्ये पण गरम करते आता कोण टाकायचं ना मधून बोलायला त्रास होतो